So welcome to today's joint colloquium. I'm very pleased to introduce Michele Cappellari. Michele did his PhD at the University of Padova, and after which he moved to Leiden for a daily fellowship, which allowed him to start working on the famous Sauron survey. After 2 fellowships in Oxford, Michele is now full professor at the University of Oxford. Today he will discuss structure of galaxies and how we use structure of galaxies to constrain or to improve better our understanding of the assembly of galaxies. So let's welcome Michele to Heidelberg.
Thank you very much, Anna, for the introduction. I hope you can hear me, and thank you for the invitation. So, as Anna said, I'm going to tell you what we learned about galaxy formation using 3-dimensional observations, and I'm going to explain later what I mean by this. Some of the topics I'm going to talk about have been covered recently in an annual review that I've written, and where you can find more details and references. So I've been asked to be general, not to assume that everybody knows about galaxies. So I'll give a general introduction of what we know and the general framework of galaxy formation, which will be familiar to people working on galaxies, of course, but probably not everybody. So the broad picture that we have, the paradigm we have for how galaxies form is a universe dominated by dark matter of completely unknown nature so far, and the universe starts with a smooth distribution of dark matter with only primordial fluctuation, density fluctuations, and these fluctuations grow by gravitational instability to form bigger and bigger clumps. So it's the dark matter that is driving the evolution of galaxies. Without the attraction of dark matter, without the creation of dark matter potential well, we wouldn't know how to form galaxies. And in fact, in the paradigm, the gas that forms a minor components of the mass in the universe collapses, loses energy through radiation, and conserve angular momentum, so it sinks to the center of the potential well generated by the dark matter halos. And so these are galaxies. On the left, these are halos simulated. On the right, these are real galaxies. And the idea is that this gas form disks at the center of the dark matter halos. The disks cool down, start forming stars, and then and those stars obviously are the galaxy that we actually observe. Then the growth of galaxies is hierarchical, so smaller building blocks merge together to form bigger and bigger galaxies.
And then we have the red sequence, which is mainly dominated by what we call passive galaxies or L-type galaxies. As you see, they are red in depth. In the middle there is a minimum, which is called the green valley, and the existence of this minimum suggests that there needs to be a, well, first of all, let me say that in this general framework of galaxy growth by merger, the idea is that the passive galaxies are the end point of galaxy evolution, and galaxies on the red sequence formed somehow by merging of blue cloud galaxies. So you have, let's say, 2 galaxies merge here, and then they grow in mass, move along diagonal lines, and in the process they get passive. But if one uses models of this process, one can see that the transition needs to be sufficiently fast if you want to create a minimum in this distribution. And so if you just merge 2 galaxies, you have a starburst of star formation, and then you gently fade the star formation away, you won't create this gap. And so simulation shows that you actually need some form of feedback, something that quenches efficiently star formation so that the galaxy ends up on the red sequence fast enough to create the gap. Another thing that one can infer from this diagram is the fact that if you merge, statistically speaking, two blue galaxies of the same mass, on this sequence you grow in mass by a factor of 2, but actually the mass of the most massive galaxies in the red sequence is more massive than what you would expect from just the merging of two galaxies that lie in the blue cloud. So another thing that then one infers from this diagram is the fact that you need some merging of galaxies that are already massive to explain the most massive galaxies in this red sequence. Now, what are the two processes that one can imagine for this galaxy evolution? So we have one process is the gas accretion channel, as I call it here, and the other is the dry merging channel. So in the gas accretion channel, you will have galaxies that are original disks. They will accrete cold gas either by filaments in the stellar medium or by accreting, for example, another gas-rich galaxy. Gas, as I said before, the gas is dissipational, so it will radiate energy, sinks toward the center, and form stars toward the center of the galaxy. And then at some point there will be, as I say, some form of feedback, so you need to quench these star formations. You will start forming stars toward the center of the galaxy, but then you need to switch this star formation off. And what I'm plotting here I just put the jet, but it's not to mean that this is an actual scenario of how I expect this quenching to happen. This jet just represents some still unknown form of quenching that makes galaxies passive. And this would be, in this case, would be the jet produced by a supermassive black hole in the center of the galaxy. But the end result is that you will have a galaxy that has a larger concentration of mass in the center. So if you want a larger bulge or a larger spheroid, as shown here, and will be passive because, as I said, this form of feedback will help make the galaxy passive, and apart from the fact that also star formation, gas gets exhausted by the star formation itself. So the end result of this channel is that you start from something that has a smaller bulge, this forming stars, and you end up with something that has a bigger bulge, a bigger spheroid in the center, and it is passive. Of course, the galaxy is also expected to grow the black hole in this process, which is shown here with the black hole. The other channel is the dry merging channel, which is illustrated here with this merging of two equal or unequal mass passive galaxies. In this case, you won't have given that there is no dissipation involved, you will not have the formation of a disk, and actually the dry merger will destroy the disk. Here I show these shells, which is what simulations shows to form during dry mergers. And the end result of this channel will be something that doesn't have a disk, that is rounder than the original merging galaxies. Another thing is that this galaxy will not have a larger concentration than the previous one, and actually using just very simple virial consideration, one can find that the velocity dispersion of the stars of the resulting relic galaxy is going to be comparable to one of the previous galaxies which merged. While along this channel, you end up with something that has a bigger concentration of mass in the center, and also will have a bigger velocity dispersion, and that will be relevant later. So, but the big question is, what is the relative contribution, and when are these processes happening during the galaxy formation evolution? So, one way to try to address this question is to try to introduce some physical galaxy classification. And I'll start with this simple slide. So, this is a very trivial question. What is the shape of elliptical galaxies? So we see many galaxies in the sky that look like just featureless, roundish objects, and these are Hubble called them elliptical galaxies because their isopods are generally approximated with ellipses. Now, so it's like observing this object like that, and assume we are seeing this from the top. Another question that we are trying to answer is, is this just a face-on, a top view of something that is flat disk intrinsically, or is actually a sphere? So now, even though this is totally trivial, if you could just fly to the galaxy and look at the galaxy from another direction, the answer to this question would be obvious. But in practice, that's a very difficult solution because we cannot observe galaxies from other directions. So we can try to address it statistically, and people have tried to do that. But the problem is that the galaxy properties changes as a function of galaxy mass, for example. So the shape changes as a function of galaxy mass. And so in practice, statistical means it's difficult to find a solution to the shape problem of galaxies. It has, however, profound implications because obviously, a galaxy like this clearly cannot have formed through the trimergent channel, while a galaxy like this is clearly a relix can only be explained as a relix of the trimergent channel. So there is you need to have in this case formation of a disk in this situation. Now, this trivial concept, of course, was very clear to Edwin Hubble. He introduced this famous Cunning fork galaxy classification diagram. Many of you will know this, but for those who don't, here we have the elliptical nebulae called at that time, the galaxy we would say today, and here we have spiral galaxies, unbarred and barred galaxies. Hubble introduced in a written form his classification in 1926. Not many are aware that actually Jeans in his book was the one that first introduced the idea of using some sort of Cunning fork or Y-shaped diagram to describe galaxies. By the way, luckily smoking is not as popular these days in our faculties as it was at that time. But anyway, the point I want to make here is that Hubble classified elliptical galaxies according to their shape. You see, E0, E3 is 7. This is the ellipticity 0.007. But he was well aware, of course, that this is just a projected shape and not the intrinsic one. And he's discussing this aspect, of course, in his paper. He's aware that there's a limitation of this classification, but there was no solution. And there hasn't been a solution for almost a century. But now, actually, the fact that we can observe 3 dimensions of galaxies is actually providing a solution to this decades-old problem. Now, this slide I'm explaining briefly what is integral field spectroscopy, for those who don't know. The idea is that you have an image of a galaxy, and then you split your galaxy, the plane of the sky, or the galaxy in a set of apertures, and then from each aperture you can, in this case with the lens array, you focus you have a lens, so you focus the light from that aperture in a small area of the CCD, then you disperse the light and you produce a spectrum at every spatial position. There are different techniques. Fiber array, in this case you have a fiber that actually physically go through each aperture, and all fibers arrange the spectra parallel on the CCD. In this way, when you have image slicer. So, but the point I want to make here is just that you have a technique that allows you to add the third dimension to galaxies. So, the two dimensions are, of course, the x and y coordinates in the plane of the sky, and the third dimension is the wavelength. So, this is what we call the data cube, and as I said, this is a three-dimensional quantity. Now, what is relevant for this talk is that the data cube allows you to get then velocity or get stellar kinematics on galaxies together with their images. So this is an image of an elliptical galaxy, and now given that at every position we can obtain a spectrum, from each spectrum, at every position we can measure the Doppler shift, and from the Doppler shift we measure the mean velocity of the stars along that position. So the end result is that we have a map like this. here the colors represent velocity of the stars, not of the gas. And red means that the stars on average are moving away from us. Blue means the stars are moving on average towards us. Now, why is velocity helping us addressing the shape of galaxy problem? This is illustrated here. On the left, I show the trivial case of a spherical galaxy that is not rotating. So in this case, the galaxy obviously looks the same, whether it's seen at 90 degrees or almost face on at 20 degrees. And in both cases, there is no rotation. So the galaxy looks green, just in rotation. Well, these are two examples of two galaxies which have two disks, which are axisymmetric and have two disks of different magnitude. In this case, the disk you can barely see from this image. It's what is called a disk elliptical. And in this type of galaxy, the disk only dominates in the central part. So when you look at the galaxy age on, you can actually see from the photometer that there is a disk, and you can see that the disk rotates fast. One can of course make models to predict the velocity of the galaxy, and what we actually observe mimics, matches very closely what we actually can predict. And in this case, this is a zero galaxy, so it's a galaxy that has an obvious extended disk. Also in this case, if you are age on, you can see from photometry the presence of the disk, and you can see also from the kinematics. Now, so if you look at galaxy all age on, then you wouldn't need kinematics to understand whether they are a disk or not. But if you actually incline your galaxies, in this case it's shown the same models but are shown at 20-degree inclination. From the photometry, the evidence of a disk completely disappears because you can make some assumptions on the profiles of disks and bulge and try to infer still that the disk is present. That problem is very degenerate. While if you look at the kinematics, you see the presence of a disk in the center parts is pretty obvious. You can just qualitatively look at the map and say, okay, this is a galaxy that has a disk, and the fact that it's round is just because it's inclined. And the same here is how this galaxy looks like when the same disk, but this strong disk is in face on. And again, you see the extended rotation. You can make simulations, and you can see that you expect to miss only about 2% of galaxies, 2% of disks due to the inclination effect. Of course, there is always an extreme case that the galaxy is perfectly face on or sufficiently face on that you don't measure velocity in the errors. But statistically speaking, your misclassification or fail just over a decade, almost 15 years ago, we produced the first maps of 48 L-type galaxies. This was the largest sample that had ever been observed. Before this, essentially nothing was known about the velocity fields of L-type galaxies. Then it took us about 7 years to move from this to a sample of 160 galaxies, which was in this case volume limited. This is what we call the Atlas of D survey. And now, but after this, things have speeded up dramatically. And now the Khalifa survey, which is one of the last first generation survey that is observing one galaxy at a time with a telescope, has produced already 600 L-type galaxies. But the real present and future is constituted by these, what they call multiplexed surveys. And the two examples are Manga and SAMI. So the key difference of these surveys is that thanks to technical advances, we don't just point each galaxy individually, but you have many IFU, many integral field units inside your field of view. You have 13 in the case of SAMI, 17 in the case of Manga. And so you can observe basically this number of galaxies in parallel. And the way to think, what this means is really totally equivalent to having 17 telescopes at your disposal in parallel. It really makes an enormous difference. And there are plans also with the Hector survey to extend this, this survey with SAMI is planning to observe 3,400 galaxies, Manga about 10,000 galaxies, and actually both surveys, they're not just planned, actually about half of the sample is available to the internal collaboration, for example, in the case of Manga, and also SAMI is more than halfway. In the future, the Hector survey is planning to extend this to by another order of magnitude even. So this then makes it possible to uncover the relics of galaxy formation process and to uncover galaxy shapes on large statistical sample of galaxies. Now, as Hubble, when Hubble first had a large number of galaxies to look at, the first thing he did, as in the slide I showed, was to just put galaxies in boxes, to look at them and try to make some orders. And we did the same when we had the first set of 160 integral fields kinematics, so two-dimensional velocity fields. And what we saw is that essentially you can separate every velocity field that you can obtain into two broad classes. One is what they call the regular rotator, and the picture by itself what speaks by itself. But these are galaxies where which are consistent with being axisymmetric. So they have a rotation that is ordered, that show no misalignment, and the photometric axis is aligned to the major axis of the kinematics. I won't go into the detail of these four different types, but all together I call them no regular rotator, and again the picture speaks by itself. They are everything that doesn't look like this. They are inconsistent with being inclined disks. So another quantity, very important quantity that you can learn from, you can infer from integral field data is the kinematical misalignment that also constrains not only the flattening of the galaxy, but tells you whether a galaxy is consistent with being axisymmetric or not. The way it works is that you take your integral field observation. Typically, in the center part of the galaxy, it's given that to obtain a spectrum, you need sufficient signal to noise. You need more photons basically to obtain a spectrum that you can use to infer kinematics than you actually need to just fill up a pixel to produce an image. So generally then the kinematics, kinematics extend to a much smaller region than where you have photometry. But what you do is you measure the axis of maximum rotation of your galaxy, and then you compare this axis with the major axis of the photometer, so the major axis of the ellipse that fits the image. Now, if these two axes are the same, means that galaxy is consistent with being axisymmetric. And so now, on a single galaxy, there is, even if you know that these axes are aligned, that tells you that the galaxy is consistent with being axisymmetric, but it doesn't tell you that the galaxy is axisymmetric. It could be a triaxial galaxy seen at some specific set of viewing angles. But actually, if you have many galaxies where these axes are always aligned, then there is no other solution than all galaxies being axisymmetric. And this is what you actually find for the full class of objects. Now, if you take, in all the diagrams, you will see blue means regular rotators, so remember the picture I showed you before, and red means no regular rotators. As you see, the regular rotator, they are all aligned, so the difference between the kinematical and the photometric axis are consistent with zero within the measurement errors. Notice that I'm plotting galaxies as a function of ellipticity, so when the galaxy is very round in projection, when you have a disk that is seen almost face on, it gets difficult to determine the major axis because the galaxy is almost round, and of course the ellipticity of a circle is ill-defined. So then you expect the errors to get bigger when the ellipticity gets smaller, even for something that is actually intrinsically axisymmetric. But when you actually, the ellipticity is small enough that you can measure the angle accurately, you see that the scattering is essentially consistent with the relative errors between photometry and while for the non-regular rotators, so the red ones, you see that there is no clear connection between the photometric major axis and the kinematic major axis. So this shows that these galaxies are actually not consistent with being axisymmetric. And actually, to understand how axisymmetric, how much axisymmetric are the regular rotator, you can compare with spiral galaxies. This is a paper in the Khalifa survey. This was Atlas E Plus pilot SAMI survey. And you can see that the scatter in spiral galaxies is actually larger than those in elliptical, well, elliptic galaxies. The reason being that spiral galaxies are colder disk, bars are more prominent in colder disk, and bars makes the photometric major axis more difficult to determine, or let's say, ill-determined question. So this shows you then that L-type galaxies, regular rotator, are as axisymmetric as spiral galaxies out to their stellar halo. So this is not a characteristic of the center part, given that the photometer is measured out to 3 half-light radius. So this means that they are axisymmetric out to their stellar halos. Another thing that you can learn from integral field kinematics is about the regularity of the dynamics of these objects. So if I take the class again of regular rotators, so the fast kinematics, and I construct some very simple models on which I will not go into any detail. I call this model jump model, G-axisymmetric models. They are models solving the G's equation. Again, details are irrelevant for this talk. The only thing that is relevant is that each model is characterized by a single number, which we call the anisotropy, that tells you how much radial orbit versus tangential orbit you have in your model. But basically, once you fix this number and you give to each model the image of the galaxy, because you want your model to reproduce the image to get the kinematics, so you play with only this number plus the inclination. The inclination, of course, is nothing physical; it's just a projection, geometric factor. So with just this single number plus the inclination, you can describe both the second moment. So this is the PRMS, or the square root of v squared plus sigma squared. The reason I'm using this quantity is essentially the second moment of the velocity, and is the quantity that the model predicts with the smallest set of assumptions. So these are the observations. The bottom one are the model, and the same for the first moment of the velocity, the mean velocity, and is again the model. The two samples are elliptical galaxies at the top, a zero galaxy at the bottom. And you see there are many differences between the individual galaxies, but actually all the differences essentially can be encoded in just this single number. So this shows that as a family, this class is really homogeneous. Another way to quantify the homogeneity of the fast rotator class is to look at their rotation. Now, in this diagram, again, I'm comparing the velocity that we observe for each galaxy with the velocity of this simple model that are characterized by a single number. Again, I won't be able to go into any detail about this, but the point is that we can predict the velocity for this very simple model, and when we compare with the actual observed one, you see that the ratio is 1 with very good accuracy. And actually, the scatter between the observations and the value of 1 is just 7%. And this includes modeling errors, because if you get the mass flight ratio incorrect while you're fitting your models, then this will introduce an error in your predicted velocity. So this shows that intrinsically these galaxies rotate in a way that is very predictable, as I say, close to this value of 1. While if you look instead of the non-regular rotator class, they clearly form a very distinct distribution, as shown in red. And there is not they're not just a tail of continued distribution of increasing rotation. There is a very clear peak, then a minimum, and then the distribution of non-regular rotator are separate. There are maximums at zero rotation. There is another, so if you want the most accurate separation between the two classes, you should use models, but there is a simpler way that you can use, which is making this diagram that was introduced in the paper by Hansen Gold 2007. So this is the specific angular momentum of the galaxy. So the angular momentum per unit mass of your galaxy as a function of the ellipticity of the galaxy. And now in this diagram, the non-regular rotator, which remember they look, they are inconsistent with being disks. They lie in this region. They're all quite round. I showed before also in the misalignment plot that the ellipticity is always quite small. And while the regular rotator, again, which look like are consistent with being an inclined disk, they form a very different distribution. This magenta line is a relation between anisotropy and an intrinsic ellipticity for galaxies that are age-on, and then the dotted dashed line are the where this age-on and a galaxy that intrinsically lies on this age-on relation would project a different inclination. You see that roughly galaxy lie in this region, which is basically qualitative confirmation that indeed these galaxies are consistent with being a family of inclined disks, as the previous evidence also suggested. Now, how does this compare with the classification that I showed at the beginning of Hubble? So, is the elliptical classification by Hubble actually physically meaningful? This plot shows that it's not. So, in particular, to get the number, you have the 2/3 of the galaxies that are classified by Hubble or the Webb as ellipticals. Actually, it turns out to be inclined disks seen at various orientation, and of course, there is a range in bulge over disk ratio. But they are not galaxies that they would look as elliptical galaxies from any direction. So they only appear elliptical because of inclination effects. More this diagram, actually the family of elliptical galaxy lie in this region. So you see that the galaxies that are intrinsically, so the slow rotator, which remember from the previous slide, they lie within this black region. So essentially all slow rotator are indeed elliptical galaxies. So given that you think those galaxies are intrinsically ellipticals, of course they will look elliptical from any direction, so it makes sense that they will be classified elliptical. But there is also a large fraction of inclined disks that is also classified elliptical when the inclination is low. So you tend to classify galaxy correctly if it's flat enough, close enough to age-on that you can actually see the disk, but when it's closer to face-on, you tend to classify this as elliptical by inclined disk. All this makes sense. Hubble knew it. The difference is that now actually we can take an individual galaxy and tell if it's an inclined disk or if it's a genuine spheroidal elliptical galaxy. Now, this is about general galaxy classification. I move now to systematic trends in galaxy properties. So another thing you can do with using integral field kinematics is to, as I showed, construct dynamical models and measure accurate masses of your galaxies. Mass is a very important quantity to relate galaxy properties. Many studies have shown that galaxy properties depend on mass. And here, in this diagram, I'm showing the mass of the galaxies versus the half-light radius, the radius of a circle that contains half of the light of the galaxy. In this diagram, I'm showing many quantities. See, this is, let's focus on this. This is the velocity dispersion as a function of mass, remember, and size. So the velocity dispersion, as you can see from the colors, lies along these dashed lines. I just illustrated, emphasized one in magenta here. So you see that the velocity dispersion, which is again another parameter that has been shown to correlate with galaxy property, follows these dashed lines so that you can follow them. You can look at every diagram and see how the velocity dispersion is expected to lie in these diagrams. So the left panel are quantities related to the gravitational potential. So this is the velocity dispersion of the galaxy. This is the gradient of the potential of the galaxy. So it's the ratio between two velocity dispersion at large radii and in the center. Well, this is the mass slope. So it's essentially a quantity that is related to the bulge fraction. So the more your mass is concentrated over the center, the redder the color here. So these are galaxies with big concentration of mass in the center. These are galaxies with shallow concentration of mass in the center. Now this quantity, the mass slope, the concentration of the potential, correlates empirically very strongly with any quantity of the galaxy related to the stellar population. In this panel I'm showing empirical quantity directly observable. This is the H beta, so it's the depth of some the Balmer absorption in the galaxy spectrum, which are tracing closely related to the age of a galaxy. Red means galaxy with weaker H beta are galaxies that are older, and stronger H beta blue means galaxies that are younger. This is a parameter that is related to both age and vitality of the galaxy, and these are galaxy colors, which is related to the mass to light ratio that you expect from your population. And as you see, all these diagrams essentially look the same, and they look the same as any of those diagrams of the gravitational potential. Also, the presence of gas in galaxies is very closely following lines of constant velocity dispersion. In this diagram, I'm showing the fraction of cold gas with respect to the galaxy mass. And again, you follow roughly these lines of constant velocity dispersion. This is what I call the IMF, that is actually the mass that you predict from dynamics, and the mass that you predict from stellar population, assuming that the stellar emissions mass function is universal. Some of you will not know what is the stellar emission function, but I won't have time to go into that. This is just mentioned for those who know. So, and these parameters are just more direct way of quantifying stellar population. So this is the age, the metallicity, and the abundance of alpha elements in galaxies. And as you see, they all again look the same. So everything traces the mass fraction, the bulge mass fraction. To just illustrate what I just said, to summarize, I'm showing here a cartoon of the same thing. So in the mass versus radius versus size diagram, galaxy lie on roughly parallel sequences. Actually, the steepness of this relation, this relation for the more passive galaxies is steeper than those for the most forming ones. So these are spiral galaxies. Essentially, along this sequence, your bulge gets bigger, and the bigger is the bulge, the more passive is the galaxy. Very importantly, however, you also have these sequences are not mass independent. In fact, you have three characteristic masses, and especially important are this mass of 3 times 10 to the 10 is the mass that separates. Essentially, below this mass, you don't have any completely passive galaxies. So you need to be above this mass to start your sequence of fast rotating passive galaxies. But another important mass is the 2 times 10 to the 11. Above this mass, you don't have any more galaxies that are fast rotators. You only have the slow rotators. So, in fact, actually, very important discovery for made possible by the integrated spectroscopy is that all the misclassified galaxies essentially, when you people for many decades thought that even here you had a number of genuine elliptical spheroidal galaxies, and the question was how to form them. Many of them were actually in the field as well, and so this was a bit of a puzzle. But integrated spectroscopy has shown that actually is virtually nothing below this characteristic mass of 11. Virtually nothing here is actually a genuine spheroidal system. They're all inclined with the parameter of the bulge fraction. And only above here you have the genuine slow rotation. This is also illustrated here in a different way. This is what I call the cone diagram, where I sort of change the handle of Hamilton in 4 to illustrate the fact that actually elliptical galaxies don't form a separate branch in terms of galaxy structure, but there is a parallelism between the characteristic of spiral galaxies with a variety of bulge fractions, bigger bulges here, smaller bulges there. They form a parallel sequence with fast rotators, L-type galaxies, which also have a variety of bulge fraction. And then there is a transition, an abrupt transition. I'm showing here there is a discontinuity as illustrated with the dashed symbols to illustrate the fact that rotators, they're always round and they're really different. They don't just extend this sequence, but there is a discontinuity in terms of their rotation. So, what do we learn from this about galaxy evolution? Well, first of all, it's really nice to be able to trace the parameters I've shown so far, and in particular galaxy classification, knowing which one is a fast rotator, slow rotator, trace them as a function of redshift, so looking back in time, we would like to see galaxy assembled and then merging, producing the two classes of galaxies, bulges growing and rotation increasing. But actually this is not technically feasible. You cannot yet obtain integral field resolved observation of galaxy at a significant redshift. The largest is at redshift about 0.1, at least until the James Webb Space Telescope, which is possible, but that telescope doesn't have complexity, so it's going to be very expensive to sample individual galaxy one by one. So, but we can do something, Pullman's study of galaxy evolution using environment, and the reason is because when you go from a low density environment from the field to the densest cluster to the nearby universe, this is the coma cluster, and in the middle you have the nearby cluster. So when you move up in number density or in halo mass, this is equivalent to sort of producing a redshift evolution. The reason being that when you move back in time, fewer and fewer galaxies are in cluster. Of course, they're not equivalent, but at least you can expect some qualitatively similar phenomena happening. So, and what is happening when you go from field to densest cluster are two channels. So the two channels that we saw in the initial slides, the gas switch bulge growth channel and the dry merger channel actually are visible in this diagram directly and are illustrated with the two arrows. So one channel has spiral galaxies, which are the green one, disappearing and being replaced by fast rotator and elliptic galaxies. Note that there is not a single red point here. They're all above the characteristic mass. So you don't form any elliptical in this process, you only form disk galaxies, a variety of orientation. So this, by the way, the fact that you transform or you have a dearth of spiral galaxy in cluster is a well-known fact. This is the Dressler morphology density relation. And then you have another channel, which is the dry merging channel that I showed before, which is illustrated with the red arrow in this plot. And what you see is that there is essentially not, as I said before, the slow rotator relics of dry merging channel only start dominating above this characteristic mass of 2 times 10 to the 11. They start appearing at 10 to the 11, roughly, and then you see that in the field, on average, masses of slow rotators are lower than what you can reach in the center of the most massive cluster. These are the two bright cluster BCG galaxies in the coma cluster. So now, the previous slide was showing data from the Atlas B survey and some observation of the coma cluster. But now this type of observation has been extended. In particular, there is a survey called MASSIVE, which, as the name says, is because it targets massive galaxies. So above these massive galaxies are the ones from the MASSIVE survey are the ones shown in black. And as you see, there is essentially they selected mass about 4 times 11. They targeted only galaxies above that mass. While the gray symbols are the same symbols that are shown in the previous plot, while the parameter here is the same angular momentum per unit mass that I showed in the previous diagram. But just to show, to explain briefly, what matters is that above this dashed line, essentially you have only fast rotators. So a galaxy that is above this line is a fast rotator, and below is a slow rotator. And you see very clearly the transition between these two that is actually very strongly confirmed and strengthened by this sample that actually targets specifically the most massive galaxies in the nearby universe. And essentially all of them, with very few exceptions, they fall within the slow rotator class. Now, I say that one cannot trace the evolution of fast and slow rotators as a function of redshift, but again, there is, and I show that one can use environment as a proxy of redshift, but there is a complementary way of doing things, which is to look at the actual redshift evolution, and this is a study by Hierarchical from the Campbell's survey. So in this survey, I actually looked at the redshift evolution up to roughly redshift of 3 in galaxies. What he didn't have is he didn't know which galaxies are fast and a slow rotator, but at least you can see which galaxy is passive, which is shown in red, and which galaxy is dark. So you can imagine that from what you see locally, you know that every galaxy here below 10 to 11 is essentially a fast rotator L-type galaxy, and these are spiral galaxies. Now, as you see, there is an evolution in the size and mass of galaxy, and a collaborator of Arjen Peter van Dokkum made a statistical model to try to describe the variation as a function of redshift of galaxy property, and he came up with these parallel tracks showing, as I was showing before, in my tracks spirals converting into L-type passive fast rotator. And here, Peter van Dokkum shows that you actually need a similar kind of tracks to go from to explain the statistical distribution that Arjen has shown in his actual observations. So let's skip this one. This is just a summary of the picture then of galaxy evolution that one consistently finds from both trying to explain observation at low redshift and observation at high redshift. In both cases, you explain the evolution of galaxies as due to a track, this gas accretion channel that I showed at the beginning, where bulge grows and the galaxy become passive. And then you have the dry merging channel, where galaxy grow by dry merging and move. In this case, actually, I won't have time to discuss, but in this case, you expect during the dry merging channel galaxy to move roughly parallel to this edge, as you actually observe. And this is the reason why your relations, essentially galaxy property, don't change along these tracks, because galaxies move with dry merging, so there is no gas involved. The stellar population doesn't change. So actually, in this diagram, often people have in the past interpret this as saying that galaxies first start as spiral, then grow their bulges, and then they merge and then transform into slow rotators via dry merging. But actually, this is not what the data shows that is happening, and the reason why this is incompatible with observation is given by the observation of environment within clusters. Now, if you look at the individual clusters, formers, Pedro and Coma cluster, in the plot, so these are very samples of galaxies with a very complete, very complete down to the same absolute magnitude. The kinematics is very good, so you have very accurate distinction between core slow rotators and fast rotators. And the selection is identical in all the clusters. What you see is that the slow rotators always lie at the center of density in the cluster. Here there is only one. It's not quite at the center. You see in this case it's slightly offset, so you want to be careful if you try to do statistic and correlate the galaxy property with actual environmental density. You will find some scatter, some offset, but obviously you expect your slow rotator to slosh around a bit near the center. They don't really sit totally at rest in the center. And similar situation in Virgo. So you have 4 slow rotators near the peak density, and then this is a well-known subcluster that is in falling, and it has its own slow rotator in the middle. And similar in Coma, you have the 2 well-known BCGs that are near the peak density of the cluster, and then another slow rotator that is in falling subclusters. So now you cannot, given that fast slow rotator are not necessarily, they overlap in mass, you cannot expect slow rotator to just go there naturally. How do you explain them to end up in that position in the cluster? So, before I explain this, let me show you another sort of confirmation or extension of the work I showed. In this case, this is a recent paper, the SAMI survey, where we observed 150 galaxies in different clusters. So in this case, the quality of the data is a bit inferior because galaxies are more distant, and also the samples are less complete. But roughly, you can think that galaxies, red colors here are slow rotators and blue colors are fast rotators. And similar to the previous slide, you see that you have again the slow rotator lying at the top of the peak of the density or in falling subclusters. So again, what I showed in the previous 3 clusters is generally confirmed. So now, how did galaxies end up there? Is illustrated with this diagram. So you need to understand and think of galaxy evolution in thinking about that galaxy evolution proceeds in a hierarchical way. And so the slow rotators, the galaxies that will become slow rotators, they start, and this is not something that you learn only from nearby observation, you learn about this from hierarchical observation. You know that massive galaxies form with very intense bursts of star formation at high redshift, and these models explain that this is essentially without galaxies, massive galaxies forming rapidly at the highest over density in the dark matter halo at high redshift. So this will be the primordial galaxy that will become the slow rotator. They sit at the center of the halo, they accrete a lot of mass rapidly, and they grow above the level above which you have 2 effects that make galaxy passive. One is the fact that you have a shock heating of the halo, so the gas within the halo becomes hot and prevents further cooling of the gas, so you stop the star formation because of that reason. And the second effect is that when galaxies grow above a certain mass, the same happens to the supermassive recovery in the center of the galaxy, and you start forming jets, which also heats up the gas and contributes to keeping the gas hot and preventing cooling. So, which means that the galaxy that will become slow rotator, they very early on in the universe, they sit at the center of the halo and they become massive. So the fast rotator will start as spiral galaxy, so they will be produced originally at the lowest density fluctuation in the dark matter halo. They will grow their mass more slowly through growing accreting mass through filaments until they are accreted by some clusters or some groups initially. But these galaxies, given that they grow their mass less rapidly and they are accreted, so they will have a higher velocity with respect to the center of the cluster, and we will have low mass. So basically they will not be able to merge, and when the groups merge themselves in this hierarchical picture of forming bigger and bigger clusters, you will have different groups merging to form a cluster. So the slow rotator, which are massive and sit at rest at the center of their halo, they will efficiently be subjected to dynamical friction, which will bring them to the center where they will slosh around for a little. They will be observed as those few slow rotators that we see in real clusters until they merge to form a bigger galaxy slow rotator. While the spiral galaxy again, they will swarm around the center of their own groups. When they are accreted by bigger cluster, they will have large relative velocity. Again, their masses are small, so they cannot sink through dynamical friction. They will just be stripped of their gas and will become passive due to environmental effect. So their mass will not grow, and they will become fast rotator galaxies. So this, the fact that these two effects essentially are happening in parallel that explain how you can have the two separate channels producing separately fast rotators and efficient. Thank you. You can have different masses in these two different disks. We call them 2 sigma galaxies because they produce two peaks in the velocity dispersion, so you recognize them from the kinematics. And they form essentially a population of galaxies that are disk but that don't follow direction.
So most of your time in explaining this, let's say, the collected galaxies and how they can form, how this is connected to random machines, fast and slow rotators. What I'm missing is how these galaxies are formed. We have all these galaxies are relatively high mass galaxies, which are in the outward. We see something about this direction.
You mean how do we start with the spirals?
Because the spiral path is just a line of spirals. Yeah. And there's not even an arrow about gas accretion or whatever, how they affect.
I'm not sure. You mean how spirals are formed in general? I mean, the way we think, but I'm not sure I fully understand the question. You mean why galaxies form relations?
Yeah.
Well, people, so let me go maybe to the one where we have the scale relations.
50% of the field galaxies are spirals.
Yes.
And also a very large fraction of mass is in spiral galaxies.
Yes. People working on simulations have shown that actually the scale relations of spiral galaxies can be explained just as a scale relation of their halos. And so if you just assume that the size of the disk scale as the size of the halo, then you do produce this naturally observed scalar relation to spiral galaxies. The way they form, they form as from the primordial gas, as this is the classic lambda CDM theory of White and Rees 78 papers, where you have this cold gas sinking towards the center of the halo and forming disks. But I'm not sure if this addresses your question.
Like you see the illusion path, but how do you get this parallel length Is the accretion going to get a constant following?
You mean how do you move from here to there?
How do you come to the other later spirals? Where are the most later spirals? Are they following smaller galaxies or are they?
But in the theory that actually was not be able to explain the rotation, scaling relation, they would just, the bigger galaxies would be just the ones that are in the biggest halo, not as big as the halo where the rotators are born, but the bigger galaxies would be in the biggest halo, so they are a bigger potential, whereas they accrete more gas in the middle, have a bigger mass, and also the scaling relations of the halo do follow the observed scalar relation of galaxies, so that it sort of fits within that picture.
Yeah. You were mentioning that this massive transform masses, and I'm wondering, and you see in this diagram, you see very much separation between those galaxies there and your spheroidal galaxies. Is that, do you actually feel like that's some kind of dichotomy, or is this not giving the full picture for us? Why what do you think is driving that? You're saying there's no passive galaxies below that, but we know there are plenty of passive galaxies below that.
Well, this is something that it's a good question. So first of all, empirically speaking, there is a transition, very clear transition where rotators dominate, but it's not an abrupt transition, so you cannot actually just separate galaxies in mass. So if you just put that mass there, your prediction of whether that will be a fast rotator is not extremely accurate. But the important thing is that you don't have a family, a population of rotator all over the masses. And the explanation for this, again, is not coming just from this diagram, it's coming also from other observations, is the fact that there are characteristic masses related both to molecular feedback and to halo quenching, which appear to require this mass on the order of 10 to the 11th in the stars. So,
and talking about the lower, this inflection, you have inflection point at that point, yeah, for what I'm trying to understand.
Okay. Well, that mass actually, okay, I understand. This is actually a good question for which I don't have an answer, in the sense that there is I've actually sort of challenged some theories to tell me why I should expect that transition mass. And nobody came out, and I'm not aware of a clean question, because indeed, in fact, it's a very important point actually, because people often, especially modelers, confuse or are unaware that there are two transition masses and not one. And people working on models often confuse the two and think that that is the halo quenching that is making those guys passive, given that this, or with the real observations. See, if you want the most passive, let's look at this diagram. As you see, the oldest galaxies indeed, they stop at this mass. And the modelers often claim that this is the stellar mass that corresponds to the halo quenching mass. But that would make sense, because there is actually the other transition above 210 to 11, which is the one that we think we have all good reason to think that is the one associated with the equations. So, as I said, I'm not aware of a good explanation why there is that transition mass, because all models predict one characteristic mass of quenching.
More questions? Yeah, please.
I was wondering if the kinematics of galaxies could be used to trace maybe the mathematical distribution galaxies.
Sorry, say again?
The kinematics of the galaxies, if you could make like rotation curves from them and find something out about the mathematical distribution galaxies.
Yes, indeed. This is something that we are doing. Yes, it's a good question. I haven't talked at all about modeling, which is something that I enjoy doing, and it's another thing that I'm working on also myself. So we did try to look at the halo distribution both of these galaxies, and also from integral field data more extended to like 4 effective radii, where you can see better the contribution to dark matter here, where you expect the halo to dominate more. The result we find is that there is a nearly universal mass slope in early-type galaxies, similar to the ones that, for those who know, that produces the flat rotation curves in spiral galaxies that has been known for a few decades. The answer is yes, we can learn about the halo from this kinematics, and it's something that we definitely do.
Last question?
Galaxies are called counter-rotating. I didn't get counter with respect to
I was thinking whether they were broad push, but unfortunately not. But so they are counter-rotating. So there are 2 disks. So the typical normally rotating galaxy would look like this one. So a normally rotating galaxy would look like this. Actually, two other figure because it's shown. So now, if you take this velocity field, you have a galaxy that is just a disk that is rotating all the stars rotating in one direction, because there is a distribution of velocity, but the mean velocity is all in one direction. And now, if you embed this galaxy into another galaxy that is also a disk, but where the stars rotate in the other direction, and the way simulations show that this can be formed is by accreting gas in the opposite rotation direction with respect to the primordial stars in the galaxy. So what you produce is something like this. So this velocity field, you see, it's another galaxy that is flat. This is what we call a 2 sigma galaxy. In this case, the rotation along the plane of the galaxy, the major axis of the galaxy, is blue on this side and red on this side. But as you move above the plane, you see that there is a reversal in the mean velocity. So here we have blue and red on the other side. So this can be explained as, and one can make actually a model, it's just a qualitative description, but one can make a model for it. One can explain as having a flatter component that is rotating, with the red moving away from us. So you have this flatter component that is rotating like that. And that flatter component is embedded in a more spheroidal one that is rotating the other direction.